Let's remember what we were talking about last Monday. We were talking about torque and rotation. So last Monday we did one of my favorite types of integrals, which was finding the moment of inertia for an extended object. Um, Today we're going to focus in more closely on torque and how to use that concept in an analysis. So we know and love Newton's second law already. And a special case of that for objects that might rotate involves torque. So the sum of torques equals, not the mass of the object, but the moment of inertia. So the moment of inertia of an object times its angular acceleration should be the same quantity as the sum of torques on an object. What I would like to do is start off by looking at what is actually one of your labs. So in the lab, we have a meter stick which is balanced at its midpoint. And we have weights hung from either arm of the meter stick. So in one version of the lab, you have a single weight that you know. You have another weight that is unknown. And you are supposed to use this setup to weigh your unknown mass. So the pivot point is put directly at the 50 centimeter mark. And your first mass, let's say, is hung from the 10 centimeter mark. And your second mass is hung from the 75 centimeter mark. Okay. So when we use Newton's second law, frequently we're actually making a static analysis where the objects are not moving. Similarly, in the lab, you're asked to play with the position of the second mass until you reach a point where the meter stick is not rotating. That is, that it's balanced on both sides. And this is actually pretty much how the triple beam balance that you use in a doctor's office works. So if we are not rotating, then that means sum of torques equals 0. In this case, we're going to have two different torques, right? One due to mass 1 and one due to mass 2. So by convention, torques that would tend to make the object rotate clockwise are negative. So mass 1 would be tend to make this sort of rotation. So that's negative, whereas mass 2 would tend to make it rotate in the opposite direction. So that'll be our positive. So our sum of torques is going to be torque due to mass 2 minus the torque due to mass 1 should equal 0. How do we calculate how much torque each mass exerts? By the way, you all have done this lab already, right? Oh, you haven't? Okay, then this must be your next one. So, what was our what's our definition of torque, right? How does a force exert a torque? So, a little bit of review from last week then, that the torque produced by a force is equal to the force cross the displacement from the axis of rotation. So this is frequently unwieldy to deal with. So we use a we use a property of cross products to make this a little simpler. That the magnitude of a torque produced by a force is going to equal F magnitude of F times magnitude of R times the sine of the angle between them. So in this case, the meter stick is free to rotate about its center, about the 50 centimeter mark, right? That's where the pivot's at, so that's where it's going to rotate around. Presumably, that's also where its center of mass is at, which is why the mass of the ruler does not cause it to rotate, because the mass of the ruler is at a distance of 0 from the axis of rotation. Now the other two masses, the first mass, its distance from the axis of rotation is 40 centimeters. Yeah? What is the distance of mass 2 from the axis of rotation? $25. That's exactly right. Okay. So then the magnitude of the torque caused by mass 1, where here we're using the magnitude version of our definition of torque, which means that we have to keep in our minds which ones are going to cause a clockwise rotation and which ones are going to cause a counterclockwise rotation. So the torque produced by mass 2 is going to be the force that it exerts on the meter stick, which is its own weight, and times the, I don't know, I said mass 2 and wrote mass 1. So its mass times gravity, that's how much force that mass 2 is exerting on the meter stick. And its distance from the axis of rotation is R2. Same thing for mass 1. And if we sum these up, we should get 0. So here our g's are going to cancel out, and we'll get something like 0.25, right? 0.25 because 25 centimeters is 0.25 meters, times m2 equals 0.4 times m1. So this lets us get a ratio of the two masses. So for example, if mass 1 was known to be 100 grams, right, then we would have m2 equals 0.4 over 0.25 times 0.1 kilograms. So we would have something like, what, 0.16 kilograms for mass 2. Does anybody have any questions about this kind of setup, using torque for this kind of analysis? No questions? All right. We're going to move on to, well, before we move on, how would we tackle this if we changed up this procedure a little bit? What if there was no mass 1? And we had only, if we had only an unknown mass, but we were free to move the location of the pivot. How are we going to attack this? Can we even attack this? Cortez, am I still recording these lectures? Yep, I am. They should all go up on YouTube. So how do we write down a sum of torques if we've only got a single mass hanging off of the meter stick? Is it possible to balance the meter stick in this way? Is it possible to balance it with a mass on the left and no mass on the right? Addison, what do you think? Oh, I was just going to ask you that, Addison. Yeah, only if the meter stick has mass. That's exactly correct. So assuming that it's a real meter stick and it does have mass, how do we take the meter stick's mass into account? Found John or Davis? Y'all have any idea? About John, Davis, Morales, or Eric? The quiet ones who've been quiet so far today. How do we take the meter stick's mass into account? How do we calculate what torque it might produce? Right, so I gave you a hint in the setup of the first part of this question. All right, Addison, since they're being quiet, do you have a guess? So you definitely could do it that way, Addison. You could say, well, all right, the we've got a piece of a meter stick on each side. So we've got a certain percentage of its mass on the left, a certain percentage of its mass on the right, and for both of those halves, the center of mass would be in the, in the center of that that length. But we could actually do it much more simply. We could just say that the center of mass of the entire meter stick is at the 50 centimeter mark. It's halfway between. And so we can pretend that all the mass of the entire meter stick is at the 50 centimeter mark. And so when we write down our sum of torques, we get the torque due to the ruler minus the torque due to mass 2 equals 0. So mr times g times this distance here, which is, 22 centimeters? So there we go. So we can deal with it in exactly the same way. So let's do one of my favorite problems. And I really like this problem because it incorporates several bits, like from several different sections of what we've been studying. And this is the fireman problem. So let's say you've got a ladder that you have put up the side of a building. And on that ladder is a firefighter. They've got on their helmet. They've got on maybe their oxygen tank. Maybe they've got an axe. So they're laden with equipment. Right. So this firefighter plus all their gear is 130 kilograms. So this is the mass of the firefighter. The ladder is only 10 kilograms. The length of the ladder is, let's say, 18 meters. And the coefficient of friction between the ladder and the ground is the same as the coefficient of friction between the ladder and the building, and it is 0.8. So my question then is, what is the maximum angle that we can get here before the, or sorry, I guess I should say minimum angle. What's the minimum angle between the ladder and the street that we can get before the ladder is just going to start sliding? Right? To get a stable ladder, right? What angle do we need to prop it up at? So, let's start by finishing our picture. What needs to go in our picture here? Eric, what needs to go in our picture? Eric, you actually here, or are you playing Overwatch in another window? Okay. I'm going to take that to mean that Eric is playing Overwatch in a different window. So, Derby, what needs to be in our picture? Right? What sort of things do we need to include in our diagrams? Just give me anything. Okay, Addison, you are not wrong. I don't know how I could have missed that we need a fire truck if we're going to have a firefighter. You are 100% correct. Spare ladder on top. Coiled hoses on the side, maybe. Basically, I have no idea what a fire truck looks like. But yes, we do need XY coordinates. I think that good old generic horizontal and vertical will do us fine here. So Derby. I don't blame Derby for not responding. I think Derby's a Mercy main, and that really needs your full attention. Wilver, what else do we need? Is anyone besides Namath, Cortez, and Sorka here? Oh, Wilver. Okay. Well, Wilver, we're not ready to do equations. We haven't finished our picture. Right? For example, there's the force on the ladder exerted by the firefighter. What's do we have more forces to put in? Morales, normal force. Yes. Where do we put normal force? I'll give you a hint. There's actually two normal forces in this problem. Well, okay, so there is a normal force from the ladder to the firefighter. But what we're mostly concerned with in this problem is the motion of the ladder, not the motion of the firefighter. Um, so where are the normal forces on the ladder? Right? So one of them is from the building to the ladder. And one of them is from the ground to the ladder. So where there's normal force, what other kind of force do we have? Right? What other kind of force is between the ground and the ladder? Friction. Excellent, Jaden. We have friction due to the normal force of the ground. We also have friction due to the normal force of the building. What else? One more force. One more force that is exerting on the ladder. Addison, you're on fire. The ladder itself has weight. All right. So if we've got all these forces drawn in, it would be a shame not to do a force analysis. So let's start there. So the sum of forces in, say, the x direction. 0 or not 0? Right? Do we want the forces in the x direction to be 0? Or do we want them not to be 0? I see some hesitation here. Come on, you've got a 50-50 shot. 0. Yes. We want them to be 0 because we would like the ladder to stay put. If it does not, the firefighter is likely to have a bad day. The forces that we've got in the x direction are, say, friction on the ground, normal force from the building. And that's it. That's all we've got in the x direction. Right? So the friction from the ground, that's going to be mu normal 2 times, and then minus normal 1. So that tells us there's this relationship between the two normal forces. So N2 equals N1 over mu. What about in the y direction? So once again, we want the sum of the forces in the y direction to be 0 because otherwise this firefighter is going to be having a very bad day. Let's rewrite it with F1 replaced by mu N1. So we have N2 plus mu n1. And we actually know the masses for everything. So MLG is 100 newtons. MFG is 1,300 newtons. So we get N2 plus mu N1 equals 1,400. How do we solve this? Right? Can we solve this? And what can we solve for? I mean, we've got N1 and N2 as our unknowns. So can we solve for them? Yeah, Jaden, we totally can solve for them. We have two unknowns and we have two equations, so solution is definitely possible. So N2 is equal to N1 over mu, so we can replace that in here. We have N1 over mu plus mu N1 equals 1,400. Or if we factor out the N1, we can say N1 is equal to 1,400 over 1 over mu plus mu. So mu is 0.8. So 1 over 0.8 plus 0.8, that's 2.05. 1,400 divided by 2.05 is about 680. Which then tells us that N2 has got to be 850. All right. Is everybody okay with this analysis so far? Or I guess what I should say is, what's the problem with this analysis? What do we not have? Right? What are we missing? I don't know. We put in all the masses that we knew. What is it we were actually looking for in this problem, though? Right? What did we want out of this problem? We weren't looking for the forces that the building and the ground are going to exert on the ladder. Yeah, we wanted to know what the right angle of the ladder would be, and none of this information has theta anywhere in it. So our analysis is good as far as it goes, but we can't be done yet because we don't know anything about that angle. For that, we're going to use torque analysis. Now, here's the great thing about torque analysis. We want this ladder to be non-rotating, right? Because we want the firefighter to have a steady, stable ladder to climb up. So in order for this firefighter to not have a bad day, the ladder needs to be non-rotating. If it's non-rotating, it's got no angular acceleration, which means the sum of torques is 0. Now, if the sum of torques is 0, then it's going to be 0 no matter where we choose the axis of rotation to be. Right? So we can say, yeah, the ladder's not rotating. It's not rotating around this point at the bottom. It is not rotating about its middle, and it is not rotating about this point at the top. Right? So 3 points that it's definitely not rotating around. Which one should we do our analysis from, do you think? Where should we put the axis of rotation for this problem? Yeah, Cortez, we could put it in the middle. We could put it in the bottom. There's no wrong answer here. Some answers are more right than others. So we know that the torque produced by a force is going to equal the force times the radius times the sine of the angle between them. So wherever we put the axis of rotation, if we put it on top of a force, that force will produce no torque. So to me then, the best place to put it would be up here at the top. Because then F1, N1, and the weight of the firefighter all produce no torque because they are right on top of the axis of rotation. Does that make sense? So you could definitely put the axis of rotation somewhere else, but you're going to have more terms in your analysis. So by putting the point up top, then I only have to look at these 3 forces and what torques they produce. So this angle here between the mass of the weight of the ladder and the ladder, that's going to be 90 minus theta, right? We can see that because if we extend this vertical down, we've got a right triangle here. So if the angle at the bottom is theta, this angle in green up here has to be 90 minus theta. By the same token, the angle between N2 and the ladder has got to be 90 minus theta as well, because we have a right angle here between the horizontal and N2. So if from the horizontal to the ladder is theta, then going the rest of the way through that right angle must be 90 minus theta. Cortez, so basically you want to maximize the number of forces you can make 0. That's exactly right. So any of those points would have worked, and any in-between point would also have worked. Like if we could definitely have said it's not rotating around this point that is 3/4 the way up the ladder. We could absolutely have said that, but it would have been a load more work. Okay. So so we're not rotating around the top of the ladder here. So this weight of the ladder itself is going to tend to produce a counterclockwise rotation, right? So we imagine it coming down and around, right? That's a counterclockwise rotation. So the torque produced by the weight of the ladder is going to be positive. And the weight of the ladder is halfway down the ladder. So the distance from MLG to the top is L over 2. So the F2, the friction on the ground, is also going to tend to make a counterclockwise rotation. It's going to tend to come out like this. So that's also going to be a positive torque. So plus, oh, I forgot the angular part. So the torque produced by the ladder's weight is be mlg times L over 2, which is the radius, times sine of 90 minus theta. For F2, we have mu n2, and the distance from this force to the point of rotation we chose is the whole length of the ladder. And then the angle between the ladder and F2 is just theta, so we have sine theta. And then we have plus the torque produced by the normal force. And the normal force from the ground to the ladder, that's going to tend to produce a clockwise rotation. So that's a negative torque. So minus n2L sine of 90 minus theta. And again, we want all of this to equal 0. So sine of 90 minus theta is kind of an awkward mouthful. How can we write that more simply? Anyone remember their trig identities? What is sine of 90 minus theta? Yeah, it's just cosine. Good job. So there is an L in every term on the left-hand side of this equation and a 0 on the right-hand side. So I'm going to cancel all the L's out. So that leaves us with mlg over 2 cosine theta plus, actually, let's do something a little clever for a moment. We're going to take this sine theta, we're actually going to move it to the other side of the equation. So we're going to have minus n2 cosine theta and then equals mu n2 sine theta. And anyone see where I'm going with this? Why did we put the sign on the other side of the equation? So the idea is we're going to take this equation and do what? How are we going to solve for theta? All right, we're going to divide both sides by cosine. Because then we have sine divided by cosine. Gives us a good old tangent. And then we can divide both sides by negative mu n2. Okay, and if we take the tangent inverse of that, we will have ourselves our theta. If questions or comments on this analysis? Yeah, if you saw it in elementary school, but we engineers now, boys. Like this is what we do. Boys and girls, sorry. I didn't mean to be non-inclusive. Uh, yeah, this is what we do. Right? People come to you and say, "Hey, is this thing going to fall down?" And it's our job to say yes or no. All right, so this is the extent of the problems that I intended to present today. We will definitely do some more on Wednesday. Yes, Cortez? Why is this one of my favorites? Uh, because it requires you to remember Newton's second law and friction and torques, right? And we have to really think about what we mean by equilibrium and stability, right? We need it to not move and we need it to not rotate. Um, yeah, and so we need to consider both the sum of forces and the sum of torques. Right, same reason that the roller coaster loop-to-loop problem is one of my favorites, because it requires us to think about the movement of the roller coaster in terms of energy, but also to analyze the loop-to-loop in terms of forces. So on Wednesday, we will do some torque problems where the sum of torques is not 0. Uh, and then next week, we will probably start on angular momentum. As usual, if anyone's got a question about the exam or the class or life, the universe, or anything, I will hang out for 10 or 15 minutes. Otherwise, I will see you all on Wednesday. Don't forget, there's going to be a little quiz. Yep, if I've done my job right, Cortez, then you will never look at the world the same way again.